Hey everybody, Mr. Smith here. In this video lesson, we're going to talk about Kepler's laws. So kind of tying it a little bit, tying a bit into uniform circular motion, gravitation, and what we learned about satellites in our last lesson. So let's get started. And we're just going to dive right in. Kepler's first law of planetary motion says that each planet moves around the sun in an orbit that is an ellipse. The sun at one focus of the ellipse. So, ellipses aren't really taught in the math curriculum anymore. But to draw an ellipse, and what makes an ellipse is an ellipse has two foci or two focuses on either side of the center of their long axis. And that kind of gives the shape of the ellipse in the following way. So if you were to connect a string between the two focuses and then stretch it tight with a pencil, if you moved your pencil all along and just kept the string tight, it would draw an ellipse. So the distance from a focus to the ellipse back to the other focus is always the same. And you guys don't really need to concern yourself with the math behind it, just trying to explain to you how an ellipse is drawn. But the cool thing about the planet's orbit on the sun is that it is an ellipse, but the sun is actually at one of the focuses of that ellipse. So that's pretty cool. A couple things to note, just some terminology. The elliptical motion is not circular. For our purposes and for a lot of the planets, the motion of a planet around our sun is for the most part circular. The difference between the farthest away they are and the closest isn't too much. So this point called the aphelion, it's the point farthest from the sun. And the perihelion is the point closest. And I just jotted this down for Earth, just to illustrate the difference. So the aphelion for Earth, the farthest the Earth is away from the sun, is 1.52 times 10 to the 11 meters. And the closest it gets to the sun is, I looked this up, 1.47. And that's not a huge difference. So yeah, I think so. Hopefully that convinces you. For us to model the Earth revolving around the sun, it does make sense to use a circle and uniform circular motion. It's not too much of a stretch. One thing to note, and this is not neat to know, but the measure that tells you kind of how much differently an ellipse is from a circle is the orbital eccentricity. And you can see for Earth, it's pretty small, 0.017. So there's not much of a difference, like a 1.7% difference. But for Mercury, it's pretty significant. For Pluto, it's pretty significant. You can see for the moon around the Earth, they're pretty low numbers. mean it's pretty much a circle. Just as a interesting side note, if you had to predict the point in this orbit, because remember this orbit for Earth takes about a year, right? What point do you think corresponds to summer, and what point do you think corresponds to the dead of winter? So it's actually interesting is that the seasons really have nothing to do with whether we're closest to the sun or farthest away, because you see it's not much of a difference. The perihelion, and this isn't the exact date, but actually the Earth is closest to the sun sometime around January, and it's farthest away sometime in June or July. It's only there's only a 3.3% difference in solar energy between those two spots. So how close we are to the sun doesn't really affect the temperature here on Earth as much as the way that the Earth is tilted and which part of the Earth is tilted towards the sun. That affects the seasons more. But that's just all some interesting stuff. What you need to know, Kepler's first law, planets move in an ellipse. the sun is the focus of is at the focus of that ellipse, at one of the focuses. Kepler's second law says that the straight line joining a planet and the sun sweeps out equal areas in space in equal intervals of time. So this visual kind of illustrates that. And so we have a little visual here, and these two separate areas represent the same chunk of time. So you can see area X is a bit, it's more kind of squash, but it's wider. Area Y is a lot thinner, but it's longer. And these two purple areas, area X and area Y, are equal. In this diagram. And so the time it takes to sweep out distance X is the time it takes to sweep out distance Y. And so there's the consequence of that. It means that planets aren't moving at a constant speed. They're moving fast when they're closest to the sun, and they're moving slower when they're farthest from the sun. So, for example, some of you guys may be interested in, watching like a lot of comets only come close to Earth, every decade or more than that. And we can only observe them from a brief amount of time. Because if you can imagine a comet is actually orbiting our sun, but its orbit is just an extreme ellipse, and it goes very far away. And when it gets close to the sun, from this illustration here, it gets really, really fast and kind of just comes in and swoops around the sun and then goes back out again. And it's very, very, very quick. So that's why Kepler's second law kind of tells us why we don't see comets. The comets are only around Earth very briefly, and then they're gone again. It's because a straight line sweeps out equal areas in equal time. Now, again, this does contradict our uniform circular motion idea if we want to treat a planet as a satellite. However, as we saw for Earth, the Earth's orbit around the sun is an ellipse, but it's pretty close to a circle. So yes, the Earth does move faster when it gets closer to the sun, and it's slower when it gets far away. But the speed for the Earth, it doesn't change very wildly, because the ellipse for the Earth is pretty close to a circle. All right, so we actually have touched on these two. It's moving fastest near the perihelion, and it's moving slowest near the aphelion for reasons discussed earlier. And we actually did touch on which days those are. It's around mid-January for the perihelion, and sometime in the summer for the aphelion. All right, guys, moving right along. Kepler's third law is kind of the law that includes like a formula and a bit of math. The other guys do as well, but this is the one we'll use to solve some problems. So Kepler's third law says that for a planet's orbit, that's an ellipse, the cube of the mean average radius. So we understand that the radius away from the sun, it does change, but the average radius cubed is proportional to the square of the period of the planet's orbit. So we're not going to prove why that is, but you could investigate that for any of the solar system data we have in our table. So this formula means this. So since r cubed is proportional to t squared, a formula for that is just this. It's for anything in orbit, r cubed equals some constant, and we're going to call it CS, times t squared, the period. And this is sometimes rearranged, or CS equals r cubed over t squared. All right, so let's just talk about what this formula means. So the r is the mean radius of orbit of the satellite. Because there's a lot going on here. There's a planet orbiting a sun, and so it's not the radius of the sun, It's not the radius of the planet. It's how far the planet is from the sun, the mean radius of orbit. T, again, because we have a couple definitions for period. T is the period of orbit. I'll say period of revolution of orbit. And this constant we call CS is called Kepler's sun constant. And this sun constant is kind of unique to each sun. So our sun has its own sun constant. And if you take all the planets, so if you take the mean radius for Earth and the period of rotation for Earth, and you calculate our sun's constant, you get a certain value. And if you use the values for Mars, you actually get the same value, more or less, and for Venus, for Jupiter, which is pretty interesting. What's interesting too is you can actually calculate Kepler's sun constant for things that aren't a sun or a star. So, for example, if we use the mean radius of orbit of the moon in the period of revolution of the moon around the Earth, we could actually calculate a Kepler's sun constant for our Earth. So that's pretty interesting. So we traditionally call it Kepler's sun constant because we're kind of modeling the planet's motion around the sun. But let me be clear, it is possible to get a Kepler sun constant for things like a planet or things like, the center of a galaxy. You can do lots of stuff with that. So we're going to play around with this law a little bit. So we can actually get a different formula for Kepler's sun constant that actually only depends on the mass of the body that's being orbited. So I'm going to show you guys that right now. So our starting points will be this. So recall. So we've already done some work with this today, but to get the period of something's motion, circular motion, we use 2 pi r over v. And now, again, we understand the motion of the planets is an ellipse, but we're now convinced that, a circle is a good approximation for that. And from our work earlier too, we know that the speed of a satellite is the root of gm over r. So if we combine those two things, we get that the period equals 2 pi r over the root of gm over r. And so we're going to just manipulate this a little bit. I'm going to square both sides. So I get t squared. And then on the right, if I square the top, I get 4, I get pi squared, I get r squared. And then squaring the bottom gives me this gm over r. And I'm just going to do some manipulating here. So this is just like dividing by a fraction. So we know dividing by a fraction is like multiplying by the reciprocal. What that does is it actually multiplies the r up top, and we get 4 pi squared r cubed over gm. And I'm going to do a little bit of rearranging here, just a tad. I'm going to actually bring the t squared to the right by dividing both sides by t squared. That's going to give me r cubed divided by t squared. And then I'm going to multiply gm up to the left and then divide 4 pi squared down to the left. And so we get r cubed over t squared equals gm over 4 pi squared. But guys, check this out. Remember, r cubed over t squared is actually the way we get Kepler's sun constant. And so this gives us an equivalent way to get Kepler's sun constant. If you want the Kepler sun constant for our sun, you take g, you multiply by the mass of the sun, and you divide by 4 pi squared. So that's pretty cool. 2 different ways we can get a sun constant. And either one might be useful. If you know the mass of your celestial body, you can use this version. But if you have information about its period and its orbit, how far it is from the sun, you can use the other version. So I think we're going to play around with that right now. So we're going to find our sun constant 2 different ways. We are going to use the values for Mercury. And I don't know why. I think everybody here probably understands that Mercury orbits the sun. But and then we're going to use the sun's mass. So the first way we're going to do it is we're going to do r cubed over t squared. So To find the Kepler sun constant this way, you need the data of something orbiting that sun. And so Mercury will do just fine. For Mercury, the mean radius of orbit is 5.79 times 10 to the 10. And we'll be cubing that. And the period of revolution for Mercury, 7.6 times 10 to the 6. And you'll notice what's going to wind up for the units is we're going to get meters cubed per second squared for Kepler's sun constant. So let's crank this out. 5.79 power of 10, and we're cubing that, divided by 7.6, 6, and we're squaring that. So Kepler's sun constant for our sun, about 3.36 times 10 to the 18, and the units are meters cubed per second squared. We can also get it using our other formula. So CS equals GM over 4 pi squared. So check this out. So G, 6.67 times 10 to the negative 11. Mass of our sun, 1.99 times 10 to the 30. Over 4 pi squared. And we should get something pretty similar. Might be a little different because Mercury's orbit is more of an ellipse than other planets, than most other planets anyway. 6.67 11 times 1.99, 30, divided by 4, divided by pi squared. Well, it actually did a bang on job. 3.36 times 10 to the 18, and then the units are the same, meters cubed per second squared. So that's pretty cool. Maybe before I go on, let me ask you guys, if I wanted you to, if I asked you to use method 1 here to find the Earth's sun constant, using method 1, how would you do it? What values would you look up to calculate Earth's sun constant? And if you said, so for the Earth, if you said you would need the information, the mean radius of orbit for the moon, divided by the period of the moon's revolution, then you'd be right. Using method 1, you need something orbiting that body. If we were to do this using method 2, if we plugged in the Earth's mass here, that would give us the Earth's sun constant. So I think we're going to look at one more example. So using the answer from our second example, we're going to calculate the average radius of an orbit of an asteroid whose period of revolution is 7.5 times 10 to the 7 seconds around the sun. And we could do this with a comet that say we know a comet returns every 40 years. We could actually figure out how far away it is, or how far it gets from our sun. So let's do this one. So where's my cursor? Here, the question implies our starting point would be this version of Kepler's third law. And we know our sun's sun constant now, and we know the period for this asteroid. And so if we rearrange this guy, we get r cubed equals cs times t squared. And so to get the, I left that pretty tight. I'm just going to rewrite that. We would just do the cubed root. And yeah, let's try it out. So cubed root, our sun's sun constant was 3.36 times, that should be 18. If you noticed that earlier, I just caught it there. Yeah, it should be 10 to the 18. So 3.36 times 10 to the 18. And the period, 7.5 times 10 to the 7 seconds. Don't forget to square it. 3.3. And when you finish this, maybe compare to your solar system data and see where this asteroid is located. Times 7.5, 7 squared. We're doing third root. So about 2.66 times 10 to the 11 meters. From the sun. And again, this is on average. So if I flip to my solar system data, so 2.66 times 10 to the 11. So you can see this is a little bit farther out between Mars and Jupiter, which kind of lines up. The asteroid belt is kind of just outside of Mars. And so that answer we got makes a lot of sense. Right, guys, that kind of concludes Kepler's laws. So hopefully you found that lesson not as intense. You know, some of our days will be a bit more intense and some of our days won't be. In my opinion, today on gravitation, satellites, or the stuff we've done, gravitation, satellites, and Kepler's laws is really interesting, but also it eases off the gas pedal as far as the math goes. So I really enjoy it. So at least for the people doing summer school online with me right now, that concludes our unit on uniform circular motion and gravitation. So as usual, you'll have a little, I'll have an assessment for you guys to do on the day's stuff to see how it went. And review is available and our test should be getting posted soon. But what's up next? Our next unit, we're going to extend our knowledge of work, energy, power. So in the grade 11 course, you guys talked about kinetic energy and gravitational potential energy, conservation of energy, the work energy theorem. But we're going to take it a bit further. We're going to look at springs and elastic potential energy. And we're going to update our knowledge of gravitational potential energy. It's going to be a lot of fun. So that's it for now, guys. Hope you're staying well. Have a great day.